Talk about GPU programming in the CUDA environment, and I would encourage you to watch the CUDA hardware video if you haven't seen that already. I'm going to assume that you have a basic understanding of the layout of the SM and SP and so forth within the GPU. So go take a look at that if you haven't watched it already. So just some basics here. Want to make a distinction between the two processors that are going to be in play here. And we're going to refer to them by their generic terms, which is host and device. So the host is basically the CPU in the system. It's going to have host memory that's going to be located on the motherboard of the PC, for example. And then the device is the GPU. And in many configurations, that's going to be a separate board that's plugged into the backplane of the motherboard of the CPU. And it has the GPU on it as well as dedicated memory for the GPU that's called device memory. And then the key steps in a typical CUDA program are three. We're going to assume that we have a GPU that doesn't have the latest and greatest kind of unified memory architecture going on here, which is consistent with the lab machines that we have as of this talk. So we've got to manage memory between the host memory and the device memory ourselves. So the typical stages in a CUDA program is, first of all, we're going to copy the input data from host memory to device memory. It's called a host to device transfer, obviously. We might have read some of that data off of disk, for example, on the host to start with, and then we want to send some of that data to the GPU, so we explicitly copy that content over to the device memory. Then we're going to invoke the GPU program, what we'll call the kernel, so the code that actually runs on the GPU itself that's going to manipulate the data in device memory that we just loaded, and do that all really fast in parallel. When that's complete, then we want to get the results back from the GPU, and we'll have to do a copy in the other direction from device memory back to host memory, or a device to host transfer. So that's the typical super high level view of how we are going to program our GPU, distinguishing between the host and the device. Obviously, there's code that's going to run in both places. The program that loads information off of disk, for example, into host memory is an ordinary C program that runs on the CPU, and then we're going to also have code that we're going to write the kernel that's going to run on the GPU. Because we're going to have code that runs both on the host and on the device, we're basically going to be programming two different processors. Rather than having to do that in two separate source files or with two separate compilers, the CUDA environment includes a compiler driver called nVCC. This is kind of the moral equivalent of the GCC compiler driver that you're familiar with, which runs the preprocessor, runs the compiler, runs an assembler, runs a linker, right? It's a bunch of steps underneath the hood there that are kind of orchestrated by GCC. It's quite similar with nVCC, except now in addition to the usual steps, we're going to be compiling some code that's going to end up running on the host and other code that's going to end up running on the device. So the compilation steps here are really kind of two. When we're running nVCC, we're really doing this first step, what I've marked here as offline compilation. So in other words, compilation that takes place before you actually execute the code. And the compiler needs to be able to arrange to compile two types of code that's going to run on the host, on the CPU, and code that's going to run on the device or the GPU. So that host code is largely going to be compiled without a whole lot of difference in terms of the basic functionality for the host machine. It is going to have to be modified a little bit to be able to launch the kernels. So when we talk about the execution configuration and the goofy triple less than, triple greater than syntax, that's what I'm after here. It's going to convert that into code that's going to enable the host to start that kernel on the device. But for the most part, it's just doing an ordinary x86 style compile down to an executable format. We also are going to compile the device code. Rather than going directly to a native assembly language or machine language that will run on the GPU, we're actually going to compile it into a kind of a device-independent format called PTX, which stands for Parallel Thread Execution. And this is an NVIDIA specific thing that is a kind of a sort of a pseudocode or pseudo-assembly code that is designed to allow code to run on different types of GPUs over time. So we might compile this down into PTX format, and then in another step, it'll be translated into something that can run on the actual GPU. And the idea here is that this PTX format is stable across different generations of the GPU. So in the hardware discussion, we talked about Tesla and Fermi and Maxwell and so forth. Those different generations presumably could have different implementations of these PTX instructions, and the fact that we're compiling to PTX instead of to those specific underlying binaries means that the code is going to be portable across different machines. That final step then that's necessary to convert from the PTX format into the native executable format on the GPU is the second type of compilation, which I've labeled here just-in-time compilation. So at the time that the program is run, we're actually going to translate that PTX code into native code for that particular GPU. Basically what this provides is kind of an interesting terminology here. We're used to thinking in many cases about backward compatibility, right? Are we still supporting the old stuff? The idea here with the PTX just-in-time compilation is that we're supporting sort of future compatibility. When nVidia come out with a new graphics processing unit that might have a different underlying assembly language, we can convert from PTX to that new architecture without having to make any changes to our program. It all hinges on the runtime environment supplied by nVidia to do that job, and our code doesn't have to change at all. Let's spend a little time talking about the execution environment in which our code is going to run. First of all, we're going to detail the idea of a kernel a little bit more. So the kernel, as its name implies, is kind of the core code that's going to run on each of the GPU cores on the GPU board itself. So you could think of it as the function that you're going to invoke on the GPU. It's going to run in each of the threads on the GPU itself. It's kind of like the, going back to the pthreads idea earlier in the term, it's kind of like the start function that gets invoked in each of the threads as they're created by the runtime environment. Here we're going to send this kernel code to the GPU, and it's going to be executed by all of the GPU cores to solve our problem in parallel. So the idea here is that this is the parallel portion of the application, and it's going to be executed k different times simultaneously, where k is the number of different CUDA cores that we're running. Or CUDA threads that we're starting up. We're going to talk about the difference between threads and cores here in a bit. But this is the fundamental unit of concurrency here in a GPU program. The kernel is going to be executed many times in parallel on different portions of the data set to calculate the results simultaneously. This next slide illustrates kind of the process of putting those kernels into execution on the GPU. So the kernel itself, that's our program that's going to run on the GPU, is going to execute in the context of a thread. And a thread here in CUDA is quite similar, as I mentioned before, to the notion of a thread in the pthreads model. It's an independent thread of control that runs the kernel code in a unique way for a particular subset of the data. Now, in order to provide a kind of a coherent interface between our program and the execution environment, the CUDA platform introduces a couple of additional abstractions. So we have that fundamental notion of a thread, which is running the kernel. But those threads are then further grouped into what are called thread blocks, also often just called blocks. And those thread blocks are furthermore grouped into something called grids. So when we're talking about executing a kernel, it's going to run on one thread, but in terms of managing the execution of our parallel program on the GPU, that kernel is going to be executed as a grid containing blocks of threads, each of which has some number of threads. And this illustration here is supposed to illustrate that. The little curvy arrows inside of here are intended to be single threads, and you can see that those are grouped into multiple blocks, and then those blocks are grouped into a grid. And what we'll see is that we can launch our GPU code in different ways by specifying the sizes of these blocks and the grids in which they're contained. So we have a lot of flexibility. Even once we've created a fixed piece of code that's going to run on one of those threads, we can actually invoke it in different ways to take advantage of the underlying hardware that's available to us, and also taking into consideration the problem size. And we're going to take a look at some of the details of that. But this is the kind of the key thing here. The kernel code is executed on a thread, which is contained within a block, which is contained within a grid. Now, referring back to the discussion about the hardware of the CUDA environment, trying to show here the notion that we can take the threads, this kind of abstract thread hierarchy that we just described, and map that onto the actual GPU. So an individual CUDA thread, one instance of that running kernel, is going to be mapped onto a single CUDA core. So one of the SPs within the SM, one of the streaming processors within the streaming multiprocessor. Then a thread block is going to be mapped onto an SM. So here's this is this streaming processor. Here's the streaming multiprocessor. So that block of multiple threads is going to be given to an instance of the streaming multiprocessor. And then because we have multiple streaming multiprocessors on the CUDA device, we can actually run multiple of those thread blocks by grouping them together into a grid. And then that entire grid is going to be assigned to the GPU. So when I first mentioned the notion of threads and thread blocks and grids, that seems kind of arbitrary in a way, right? There's nothing inherent in running a parallel program that requires us to group things in that fashion. But the point of those logical groupings of our execution model is to provide a nice way for the runtime environment to map it to the actual hardware. So we get a little bit more visibility into the structure of the hardware, which is why I wanted you to learn about the CUDA hardware before talking about the programming model. But that's exactly what's going on here. We've got this kind of nice symbiosis going on between the execution model of threads, blocks, and grids and the underlying hardware that's going to run those threads on each SP grouped together by SMs, and then those SMs are collected together on the GPU itself. So here's a little decoder table again. Threads go to SPs, the CUDA cores, blocks go to SMs, and the grid goes to the GPU itself. So at runtime, this is kind of, I guess, another just simple summary of what goes on. The CPU is going to kick off from the host side, right? That's the CPU. The host is going to kick off the execution of a kernel grid. So a grid containing blocks, containing threads that run kernels. Within the grid, different blocks are going to be split up by streaming multiprocessors. So each streaming multiprocessor is going to be responsible for executing some collection of blocks of threads. And then within those blocks, we're going to concurrently execute on all of the streaming processors within that SM, the threads from the thread block. One of the interesting things about that approach to distributing the work, and again, this is part of the goal that nVidia has of making it simple to move code from one style of GPU to another, or one architecture of GPU to another, is that the software doesn't have to know explicitly what the particular capabilities of the underlying GPU are. So this is an illustration here of kind of this behavior at runtime. So up here, we've got a representation of our CUDA program, sort of writ large. And what we're showing here is that the programmer has opted to divide the functionality of this CUDA program into 8 blocks, numbered 0 through 7. Now that's something that's just specific to the code, right? It's the way that the programmer has chosen to have the host invoke the underlying kernel code. But the programmer doesn't know necessarily what kind of a GPU that code is going to run on. So for example, down this left arm here, we could imagine that we have a GPU with just 2 streaming multiprocessors. So we've got SM0 and SM1. We can't run all 8 of these blocks of threads simultaneously, but the GPU runtime environment is going to take pairs of these and run them together. So what we're seeing here is time advancing down the page. First of all, we're going to use these 2 SMs and we're going to schedule block 0 and block 1 to run. So those 2 blocks of threads will run. When they're completed, then the runtime environment will schedule blocks 2 and 3. When they're done, blocks 4 and 5, and then blocks 6 and 7. So we're taking advantage of as much parallelism as we can. We've got 2 SMs. We've got at least 2 blocks. Let's run them 2 at a time. So we're taking maximum advantage of the performance. And it's going to take, sort of 4 units of time to complete that calculation. On the other hand, if we have available to us a GPU that has 4 streaming multiprocessors, well, now we can take those blocks 4 at a time. So we're going to take, in the first gulp, the first 4 of those blocks and execute for presumably the same amount of time as we did when we were only able to handle 2 before. And then we're going to do the other 4. And after sort of 2 units of time, we're going to be complete, having executed all of the threads that were determined by the CUDA program itself. So again, there's this nice kind of isolation layer between the way that we develop the code and the way that it's actually executed, depending on the specifics of the execution environment, and in other words, the capabilities of the GPU itself. Here's some further comments on this ability to kind of automatically scale to use as many streaming multiprocessors as are available to us. So first of all, CUDA does do this scaling as we add the number of cores, as we've just seen. In order to accomplish that, we have to write our program using these CUDA abstractions. We have to be able to tell the processor where the kernel code is. We have to invoke it using an execution configuration that we're going to talk about in a second, in order for the runtime to grab onto that and choose how to actually deploy it out to the GPU for calculation. As always, we're using a divide and conquer approach here. We're going to have some large data set that we want to process quickly, and we'll see some strategies for how do we take and partition those data into smaller chunks that can be assigned to individual threads running our kernel. So that's no different than the other paradigms we've explored this semester. The pthreads model, we gave a piece of the data to each of the threads. In the MPI model, we gave pieces of the data to each of the underlying MPI programs. Same thing here. In order to go fast, we want to do a bunch of calculations simultaneously, so we're going to split up the overall data set into smaller pieces and give each of those pieces to an individual thread within a thread block. Then each of those blocks is going to solve that sub-problem by running that kernel on all of the threads. And the CUDA runtime, importantly, is going to be responsible for doing that scheduling, right? We don't have to know, again, back to this illustration, we've set up 8 thread blocks in our implementation, and we don't have to know or care really how that's actually run on hardware. The runtime environment is going to take those 8 blocks and split them up appropriately to take maximum advantage of the computing capability of the underlying GPU. One of the things that's important to keep in mind there, because the runtime environment and the hardware on the GPU is going to be responsible for scheduling these different thread blocks to run, we don't know in advance what sequence that's going to take. And I'll show you an example of that here in a bit. But we need to make sure that in order to get our programs to scale to any number of multiprocessors, our kernel code cannot rely on a specific sequencing. Back here I'm saying, well, it's sort of arbitrarily, this illustration shows block 0 and then block 1 running and then block 2 and block 3 running and so forth. But that is not guaranteed by the runtime environment. It might run blocks 1 and 4 and then run blocks 0 and 7. We can't write code that is contingent on a specific sequencing of those blocks being executed. Our kernels have to be written as if they're just independent pieces of code that are going to solve a specific subset of the problem without any dependency on ordering. If we somehow introduce that kind of a dependency, it's not going to work properly. So that is kind of the cost we're paying for this ability to scale up to any number of multiprocessors. Now let's take a look at some of the details of how we code these things. So first of all, we've been talking a lot about the kernel, and we've seen some examples of that already, but what are we really talking about here? Well, the kernel is just a C function or C++ function, and again, it is the fundamental unit of parallelism in the GPU environment. So we're going to have that same kernel code running n times on each of the n threads that are going to be executing our code. And because those threads are going to be run simultaneously on many multiprocessor cores, we're going to get parallelism. We'll see that we have to declare these kernels specially. You've seen examples of this already with this __ global __. Some people call these 2 underscores dunderscores because they're double underscores. I'll probably use that awkward abbreviation. And then we also need to, at runtime, tell the CUDA environment how we want to partition the problem space in terms of the number of blocks per grid and the number of threads per block. And that's going to use this crazy less than thing. We'll look at some examples. So here's a super simple kernel. It's a vector addition kernel. First of all, you can see that it's the function declaration is prefixed with that underscore global construct. That just tells the compiler, the NVCC, hey, this is code that's going to be running on the GPU. It also is going to allow the CPU to call this function, right? So this isn't code that's going to run on the CPU, but when we invoke this function, it's got to have to be known to the host code. So that's why it's called underscore global, even though the code itself is going to run on the GPU threads. And this example, vector add, we've got 3 vectors that we're passing here, pointers to arrays of floats. And basically what we're going to say is calculate the value in an element of the C vector that sums the value from A and the value from B. So the business end of this function is just to say, take the ith element of A and the ith element of B, add it together, and store it in the ith element of C. Now that's the fundamental computation that we're doing in this kernel, right? Is just adding those 2 values to come up with the sum. And importantly here, we're also expressing kind of the unit of parallelism. We're saying, hey, each of the streaming processors in the GPU running all of these threads is going to do that one fundamental operation. Get something from A, add it to something from B, put it in C. Now the question though is, which something from those 2 arrays are we going to add together to put into the corresponding location in C? Well, that's being determined here by this thread index.x, which we're going to unpack in a lot more detail here. But basically what that's going to do is give us a unique index into all of the elements of the array. And we'll see how that shows up in a second. And then we're just grabbing that value, putting it into a local variable, and then using that to index the array. So we might have a 10,000, 100,000 element array here. We're basically saying I want each thread on each SP in the GPU to add together one of those pairs to come up with the sum. And they're all going to run simultaneously. Importantly, if there's more threads, in other words, more elements of the array than there are SPs in the overall GPU, that's still going to work fine. The runtime environment is going to schedule some of those threads to run, and when they're all done, it's going to schedule some more threads to run, so that we're eventually going to have a situation where some thread is going to have all of the appropriate values for thread index of x to add all of the elements of both arrays together to give the sum. So that's the kernel. And this is a way that we might invoke that kernel. I'm leaving out a bunch of stuff here, obviously, but here's our main function. So this is host code, and what it's going to do is invoke that vecadd function, the kernel function. Again, this is why we call this a global function. It's going to really run on the device, but it's going to be invoked on the host. And we're going to pass in 3 arrays, right? A, B, and C. And we'll see that we have to do some other monkeying around to set up those locations in memory and so forth. But the interesting part here is this first, or this execution configuration, this weird triple less than, triple greater than syntax. What this is telling the runtime environment is 2 things. Remember that we have grids that contain blocks that contain threads. Right, and this is the code that's going to run on each of those threads. So these 2 numbers that we're passing in the execution configuration have to do with the number of blocks per grid and the number of threads per block. So the first of these is the number of blocks per grid, and I'm just basically saying I only want one of those. But then I want to have n threads per block, right? So whatever n is, and presumably this has been passed in as a constant, or it's a sharp define or something like that. But n is the length of each of these arrays, A, B, and C. So I'm saying I want you to run n threads and do these calculations on each of those n threads within a single grid. Now there's some issues with that in terms of sort of the limitations associated with how many threads you can actually put in a block and so forth, which we're talking about in a little bit. But at least in principle, we can just run one grid and have as many threads as we want. It's actually limited to 1,000 threads. So if we have really big arrays, we're going to have to come up with another way of handling this that doesn't require us to allocate more threads than are available to us. But to a first approximation, we're just saying this is the number of blocks per grid, and this is the number of threads per block. And we're going to come back and talk about this in a little bit more detail. It's actually more flexible than just a single number. So I've already talked about the fact that we are grouping together both the host code and the device code in the same source file. You'll recall from previous homeworks that these are all going to be grouped together in a file with a .cu extension or multiple files. That's just the .CUDA extension. And we have to tell the compiler, the NVCC compiler, which code is going to run where. And that's the reason we have this global here and nothing here. So there's three possibilities. We can say that we want to have the code run globally, which is what we've seen. So that's going to be executed on the device, but it's going to be invoked from the host, right? This code is executed on the device. It's being invoked from the host. If we want to specify a particular function is going to just run on the device, we can prefix it with the _ device prefix. And that's going to say basically we want to run this on the device and we're going to call it from the device, right? So we don't have to have just one monolithic kernel function that's the one that we declared to be global. We can use ordinary software engineering practices and decompose the functionality that's going to run the GPU into many different functions if we like, but we need to tell the compiler, hey, those things need to end up out on the GPU at runtime. So we need to prefix them with this device keyword. And then we can also, if we want, prefix a function with the host keyword, and that's just run on the host and called from the host. So it's just an ordinary function. And this is the default case. So the reason we didn't have to tell the compiler that main was going to run on the host is because we didn't, without any decoration at all here, it just runs on the host. So if you want to explicitly state that this particular function runs on the host, just to make things clear, that's fine. But the default, if you don't say anything else, is going to be to run on the host. Okay, now that runtime configuration, we kind of looked at a very simplified version of that, where we were basically just saying a specific number of blocks per grid and a specific number of threads per block. It's actually more general than that. Now, if we take a step back and think about what kinds of problems we're typically going to execute on a GPU, certainly in the sense of the original purposes of GPUs to do graphic stuff, we're thinking about one-dimensional vectors, we're thinking about two-dimensional arrays, like representing a surface or a screen, or three-dimensional volumes that we're trying to model and use that information to render to some pixels that are going to show up on the screen. So we have this ability or this need to be able to deal with things that are one-dimensional, two-dimensional, or three-dimensional. And the values that we can pass in this execution configuration or runtime configuration reflects that. So in general, I just have like d sub g and d sub b. So the dimensions of the grid and the dimensions of the block are what those are intended to convey. So these guys can be one of two things. They can be an integer, which is the example that we just saw previously. And in that case, we're basically specifying a one-dimensional vector, right? Just a single one-dimensional array. But if we want to be able to compute using two-dimensional grids, like to do a matrix calculation, for example, or three-dimensional volumes containing information about a scene that we're trying to render, we can do that as well. And instead of using just an integer, we use this data type that's defined by the CUDA environment called the dim3. So it's a three-dimensional thing. And what we'll see here is that so first of all, these are built-in types, and they allow you to index and group together one, two, or three-dimensional blocks of threads or grids of blocks. So we can do any dimensionality that we'd like in there. And you can see that this integer case is kind of the simplification of that. If we're talking about a one-dimensional vector, what we're saying is along the sort of we're looking for n elements along the x direction and 1 along both the y and the z direction. So it's kind of a degenerate case of the three-dimensional volume. Let's look in a little bit more detail at these dimensions for grids and blocks, so dg and db. These behave like structures in that you can reference elements within them called x, y, and z. And when we talked before about this sort of schematic example here where we were launching a program that had 8 blocks in it, what we're saying there is that we as the developer can determine how many blocks we want to partition the work into, and then we can hand those blocks off to the CUDA environment at runtime to let them execute on the SMs and then the SPs within those SMs. In order to specify the number of blocks, we're going to use this d sub g argument to the execution configuration to specify the dimensions of the blocks within the grid. And that's going to give us a total number of blocks. So if we multiply together dg of x, dg of y, and dg of z, the product of those things is going to tell us how many blocks we're going to execute within this grid. So all those blocks are going to be shipped off to the GPU and then be executed. In addition, we also want to talk about how many threads are going to be available per block. So the d sub b, the block dimension, is going to specify that. And it also has an x, a y, and a z. So we can say I want to have, if I'm trying to model a volume in the threads that are running inside of that thread block, I can specify the dimensions of that volume using those parameters. And the product of those is going to tell me how many threads I'm running per block. It's important here, I've highlighted it, that you keep in mind that all of the architectures from nVidia so far have restricted the number of threads per block to 1024, 1K. So you can use any combination of X, Y, and Z that you want in there for the sizes of the numbers of threads per block. But if the product of those things exceeds 1024, you're going to get some errors from the CUDA environment. And notice again that you can run a bunch of these blocks that have the same shape. So we can have a total number of threads that is really big, that is bigger than the number of SPs that we have on our on our GPU. And the runtime environment will stream those different blocks through the GPU as quickly as possible to take maximal advantage of all that parallelism. And it's pretty easy to calculate that, right? We know how many threads per block we're going to have based on the d sub b, and we know the number of blocks per grid we're going to have based on the d sub g. So the total threads that we're asking to have executed is just going to be the product of those two things. Now all that is something that the host is paying attention to, right? This is the runtime configuration that you're going to use to invoke the kernel from the host code. So this is all information that needs to be known to the host. We also have to be able to be aware of how the kernels were actually executed from inside the kernel so that we can behave appropriately. So the host launches the kernels on the device, but the kernels need to know about this runtime configuration. And there's not an a priori way to do that like at compile time, because these variables that are passed into the execution configuration are variable. We could actually specify them at runtime. If we read in a big matrix we're trying to do some operation on, and we don't know until runtime how big that matrix is, we can still do some arithmetic to figure out how we want to split that up onto blocks and threads. And that's not a compile time thing. So the kernels also have to have some way of accessing the information about the execution configuration at runtime. So the compiler arranges to add to your kernel code access to what the documentation just refers to as built-in variables. And there's 4 of them, and they all have this same shape. They have .x, .y, and .z elements, so that if we're spinning up a kernel that's intended to run against data that's in a 3-dimensional volume, we can use that information conveniently. So these are the 4 variables that are available to us. So one's called grid dim, and that's the dimensions of the grid. It's basically the information that got passed in here in the d sub g argument. There's a corresponding block dim called that's also a dim3 type, and that refers to basically the information that's being passed in to d sub b. Right, so the kernel can get a sense for the overall shape of the blocks within a grid and the threads within a block. But now for a specific instance of the kernel, a specific thread, we want to have more detail than that. And in particular, we'd like to know within a particular block, which one are we running in? There might be many, many blocks that are executed within the grid based on the host execution configuration. The kernel on an individual SP running that kernel code in a thread needs to know which block it's in so that it can figure out which portion of the data it's going to operate on. And that's what the block index variable gives us access to. And this is also going to have, as I said before, an X and a Y and a Z element. not only do we want to know which block we're in, because there could be many, many blocks, we also want to know within that particular block, which thread are we? So the thread index variable gives us a similar way of determining which thread we're in within the block. So we're exposing all of the information necessary for the kernel to be able to calculate which portion of the data it's going to be responsible for within this particular thread. Here's a very common approach to doing this. So each thread obviously has to process a subset of the data. That's the point here. So this is one way to do this. We want to calculate a thread ID, I'll call it. Now this isn't something that's specific to the CUDA environment. It's just kind of a conceptual way for us to think about how do we partition the data. If we think about just processing, say, a one-dimensional array, if I know that I'm going to run 1,000 threads, I want to partition that one-dimensional array into 1,000 pieces and give each piece to one of the threads. So by thread ID, I'm just basically saying, let's come up with a number between 0 and the number of threads minus 1 that tells this particular thread running the kernel which piece of the data do I want to get at. So we're going to take and map the block index information and the thread index from back here, right? The block index and the thread index. It tells us which block we're in and which thread we're in within that block. And we're going to use that to calculate a thread ID. And of course, we could be doing this with either a one-dimensional, two-dimensional, or three-dimensional case. In the case of an integer value being passed to the execution configuration, it's a 1D case, but we could have a three-dimensional volume that we're trying to work within. So what we want to do is do some simple arithmetic to derive a unique thread ID that gives us this range of values that we can use to reach into the underlying array. So in the 1D case, we're just going to use the x parameter, or the x element of that dimension. If we have a 2D case, we want to use the x and the y values, and we can do that by taking the x value and adding to it y times the size of that y dimension. And if we want to do 3D, we can use all three of those values and take the x value plus the y value times the size of the x dimension plus the z value times the product of the x and the y dimensions. This is actually quite similar to the kind of macros that we've used to access specific elements within a two-dimensional array. So if we think about a two-dimensional array stored in memory, and it's got some number of rows, and each of those rows has some number of columns, and we want to figure out how to get to this particular cell within the array, what we're going to do is skip down past some number of rows, and in order to do that, we have to know the width of each row, right? So if that would be corresponding to the 2D case here. We're going to take y, the second component that tells us which row we're in, and multiply it by the x dimension. And that's the number of elements in this direction, the number of elements per row. So we're going to skip past that many rows to get to this row. And then once we're at that row, we want to add our x value to skip across to that particular location within that row. In the 3D case, we're basically extending that by imagining that we have multiple planes of those same dimensions. And this product here, the z element times the dimension of x and y, basically is going to be z times the number of elements in one of these planes. So if we were looking for the 0, 1, 2, third plane, we would skip this whole plane, this whole plane, this whole plane to get to this one. And that would be exactly z times the two dimensions of each plane. And now we're on this plane, which is the one of interest, and now we're going to skip over that many rows and then skip across to that particular column. And that's going to allow us to determine a unique index that gives our thread ID in this range from 0 to the number of threads. Let me be quick to point out that when we're talking about this calculation here, going from the thread index to a thread ID, we're not talking about how we're accessing the data that's being operated on by this particular thread. We're just trying to figure out our identity within all of the threads that are running on the GPU at any particular time. Once we know that, then we could go to the actual data and say, well, I'm thread 17 of 64. I'm going to go to the 17th chunk of the data and do my thing on that chunk. Note also that I've just been kind of thinking about looking for the particular thread within a thread block. If we're running more than one thread block within a grid, we have to do a similar calculation to figure out which thread block we're in, and then given that information, we can figure out which thread we are within that block, and that will then allow us to come up with a global identifier that says we're thread X of Y. Here's just a slightly more complex example that illustrates this a little further. This is a matrix add instead of a vector add, so we're getting two input arrays that are both two-dimensional arrays of floats, and it's a square array of n values by n values, and we're going to generate a sum. So the business end of this kernel is just that addition statement. We're going to go to the jth column of the ith row from A and from B, add those two things together and store them in the corresponding column in C. And to figure out what particular element of the array we want to access for this particular thread running the kernel, we're going to use that thread index X and thread index Y to determine which one we want to access. So how is that set up here in the main function? Remember that this main function is running on the host, and it's invoking the kernel, which is declared to be global, which means it's invoked on the host and runs on the device. In our run configuration, we've got two parameters here, num blocks and threads per block. So num blocks, again, is just an integer. And what that means is that we're only going to run one block per grid. So we can kind of take the whole block dimension, block indices, all that stuff off the table. We're really just spinning up multiple threads that are going to focus on this one two-dimensional array. And that's what's being specified here in the second argument, the threads per block argument, which is finally of type dim3, threads per block, and it's got two parameters. We're basically specifying the x dimension and the y dimension, and because these are square matrices, those are the same values. And we're going to basically give one element of the underlying matrix to each thread. That's why we were using n and n here. If we wanted to do more than one of those additions within a single kernel, we would maybe spin up fewer threads and then have to index within the threads more elaborately than just having this one single instruction here. But oftentimes that's not worth it. Just let the CUDA core worry about how to execute these different threads. So what's going to happen here is that we're going to spin up n times n threads, and each of which is going to be responsible for one element of the sum. Well, which element? Well, the way that these things get invoked, the runtime environment is going to pass in the x and the y offsets into this two-dimensional grid of threads, and we can just go ahead and use that those two thread IDs to figure out which of the elements of the array we're responsible for. So I hope you can see now a little bit about why the CUDA model goes to the trouble of creating these three-dimensional structures. In the case where the thread configuration within a block and the blocks within a grid are compatible with the underlying data structure, if we create a three-dimensional structure in terms of threads within a block and blocks within a grid, and we're also operating on a three-dimensional data structure, we can use those underlying indices that are determined at runtime by the CUDA runtime environment to inform the kernel which portion of the data set it's going to interact with. Not a lot of additional monkeying around to map to the specific places in the data that the kernel is supposed to operate on. And remember that the kernel is going to be spun up many, many, many times, and each of those different invocations of the kernel on a separate thread is going to operate on a different portion of the data set. To drive this home a little further, I want to just show you some simple code that illustrates a little bit more elaborate use of these execution parameters. So first off, so here's my main function, and I'm just defining some constants here that specify the size of the blocks per grid and the size of the threads per block. So just giving these some arbitrary values. And then to be able to print some information out about this as we go, I'm going to calculate the number of blocks per grid. And we'll see here, if I look down here to the dim3 declaration of blocks per grid, I'm using bx, by, and bz. That's telling me how many blocks there are going to be in each of those three dimensions within the grid that's going to be executed. So the total number of blocks per grid is going to be the product of those things, as I said before. So bx times by times bz. And I'm going to print out that blocks per grid, and we should see that it's equal to 2 times 3 times 4. Similarly, when I declare the dim3 variable that says how many threads per block and what the dimensionality is going to be, I'm going to have 3 threads per block in the x direction, 3 in the y direction, 3 in the z direction, and I'm also going to calculate that threads per block value again by just multiplying those together, and then I'm going to print those out at runtime. The other thing I'm printing here is the total number of threads, and as we've talked about before, we've got a certain number of blocks per grid, a certain number of threads in each of those blocks, and the product of those two values should be the total number of threads that I'm asking the CUDA environment to run. And then I'm going to invoke a kernel function called whoami, and we'll look at how that works in a second, and I'm passing in these two dim3 values. So I've got a 3-dimensional collection of blocks in the grid, another 3-dimensional collection of threads within each of those blocks, and the whoami function is going to actually just give us some output to say, who am I? Okay, so when I run this program, we'll look at the whoami in a second. I want to look at the output here. So we're looking for blocks per grid, threads per block, and the total number of threads. And this is the output that we get. 24 blocks per grid, right? That's the bx times the by times the bz from back here. And then the number of threads per block is 27, right? So 3 times 3 times 3 is 27. And then the total number of threads is going to be the product of those two things. So I'm asking to run 648 threads configured as a 3-dimensional group of blocks in the overall grid, each of which is a 3-dimensional group of threads in the original block. As I mentioned before, we don't have to worry about keeping the number of threads at or below the number of actual cores. In this particular case, I'm ending up asking for 648 threads to execute my kernel, and the GPU that I'm running on actually only has 384 cores. And the runtime environment is completely happy with that. It's going to orchestrate the execution of up to 384 of those threads at a time, and when one of those gets done, it's going to go grab the next set of threads in order to complete the execution that was requested at runtime. So the CUDA can run a lot more threads than cores. Okay. And this, again, is a kind of a side effect of this goal of partitioning or separating out the specifics of your implementation of your algorithm from the runtime environment on which it's going to execute. You should be able to take that same code and run it on a bunch of different GPU configurations without making any changes at all. Okay, let's take a look at the actual kernel. Again, it's defined with a _global things because it's going to be started on the host and running on the GPU. It's called whoami. It's the thing that I invoked back here and passed in these two dim3 structures. And I want to now fish values out of those dim3 structures from these predefined variables that are set up for me by the compiler in order to give you some idea of the kinds of calculations we can do to be able to determine what is our ID, or which portion of the underlying data we should be processing in this particular thread running the kernel. So I'm going to start at the block level, and again, back here we specified blocks per grid in a 3-dimensional dim3 structure. So we're going to go, in order to calculate a block ID, we're going to look at the x value and add to that the y value times the x dimension, and the z value times the product of the x and y dimension. So exactly the calculation we were talking about before with regard to the threads within a block, you can also do that same thing for blocks within the grid. And then I'm going to determine what my block offset is, and that's going to be my block ID times the size of an individual block. So if I've got, back here we saw that we have 24 blocks per grid. I'm basically just trying to figure out what's going to be the offset for the particular block that I'm in. Then I'm going to do this similar calculation with the thread offset, and it's the same calculation here with x, y times the x dimension, z times the x times the y dimension. And then that's going to allow me to calculate my final ID value by adding the block offset, right, which is just however many blocks were ahead of me before I got allocated. And then within the block, the thread offset gives me the rest of the picture. So my final ID value here, which again I can use to figure out which portion of the underlying data I want to operate on, is just the sum of those two values. Now I'm going to print out the details underlying this calculation. Remember that this is the kernel code. So this thing is going to run once in every thread that's being invoked by the execution of our CUDA program. So this printf statement, we're going to see one of these lines of output coming from every single thread running on the GPU over the course of the execution of the entire program. What it's going to show is that calculated ID value, and then it's going to give us the details of the block index in all three dimensions, and then the calculated offset, and the values of the thread index in all three dimensions and the calculated offset. And remember that each line of the output here is coming from a single thread running this kernel. So here's an example of part of the output. So these aren't coming out in any particular order. I didn't do any sort of sorting or anything like that. Just ran that code, and this is what shows up. We can see here that this first value, the ID value that I calculated here using both the block offset and the thread offset, is 351. What that's saying basically is of the 648 total threads that were spun up by this execution configuration, this particular thread, the one that generated that one and only line of output, has determined that it is thread 351 of 648. And then we can look at the specifics of how it calculated that, where it's showing us that when it looked in the block index, it was told that it was block 102, the X, Y, and the Z values. And it uses that information along with the size of each of the blocks to calculate that 351. In this particular case, the corresponding values from the thread index were all 0, so the resulting offset for the thread was 0, and that 0 plus 351 gives us this global offset for this particular thread. The next one that we see output from has the same values for the block, but it's now a thread with an X value of 1 instead of 0. So it calculates that it's thread offset 1, and we see 352. And that continues all down this page here. You can kind of look at the pattern of the X, Y, and Z values coming from the threads. On the next page, we'll see a transition. So this takes us up through thread ID 377, and you can see that the block offset has remained the same. It's been 351 through this whole thing, and the thread offset has started at 0, and now it's gone up to 26 because it's hit the third of each of the three dimensions. Right? Remember, we made the thread block to be a 3 by 3 by 3, so the indices are going to be 0, 1, and 2. And the result of the calculation of the thread offset is 26. So we can see that we've got 27 different combinations of X, Y, and Z for the thread offset, which corresponds to that 3 times 3 times 3 number of threads per block. Then the next thread that we hear from happens to be the one from this block, the one that ends up being at offset 270, and then the threads are going to similarly be going through the same pattern that we saw for block 351, and we see 270. So these are coming out in whatever order the GPU decides to schedule and execute these threads. There's not any particular way of predicting the order in which that's going to happen, and as I mentioned before, we can't assume that because we want to let the GPU worry about scheduling these thread blocks in whatever order it wants to be able to take maximum advantage of the underlying hardware. We can't build into our algorithm anything that's dependent on a specific thread within a particular block going first before others. And that's pretty clear here in the fact that we just sort of got these arbitrary, block number 351, block number 270. There's nothing that the code is doing, that our code is doing to force that kind of ordering. It just happens to come out that way. Just a quick mention here of the way that the memory is laid out on the GPU. Each of the threads has got its own local memory. So because a thread can call functions, and we know that when we make a function call, we've got to be able to push a return value on the stack, and we've got to be able to allocate local variables and that kind of stuff. No different on the CUDA cores. They have to be able to do that, so they have their own local memory. It's also sometimes called register memory. It's right on the chip. It's quite close to the CPU or to the GPU core itself. It's really fast, and these values are all private to the thread. We can also arrange for threads within a block to share memory. So there's a shared memory mechanism that's visible to all the threads in a block. And you have to declare that memory with a particular keyword. It's _shared. And that would allow you to share information back and forth between the threads within a specific block. Now, at that level of detail, you're basically back in the same situation we were in when we were talking about shared memory programming. In particular, we want to make sure that we don't have any race conditions. If one thread is trying to write to one location in shared memory and another one is trying to do the same thing, we need to be able to avoid that. So there's some synchronization primitives and things that are available to the CUDA programmer in order to be able to do that. And then we also have access to global memory. So every thread that's running on the GPU can write out to the global memory, which is basically the frame buffer memory, or the DRAM that's on the GPU. So here's an illustration of that. Individual threads has access to per thread memory. Thread blocks have access to shared memory that all of the threads within the block can access. And then we also have a global memory space that all of the threads in all of the blocks in all of the grids that are executing currently can access. All right, let's talk about the runtime environment here. So first of all, there is a quite extensive library that gets linked in with your code at runtime to do all of the magic that we've been talking about so far. It's in a library called CUDA RT for runtime. It's set up at the time the application is initialized, and we've seen previously that one of the things that this runtime library allows us to do is memory allocation and memory transfer. So the CUDA malloc, CUDA free, and CUDA memcopy that we spoke about previously are implemented by that runtime library. It also allows us to deal with shared memory. Here's that _ shared qualifier that we can use if we want to be able to access this type of memory across the threads in the same block. It also has some additional functionality to allow us to do some asynchronous things. So we can actually have the host doing computation while the device is doing computation and vice versa, and then synchronize back and forth and transfer data that we've already discussed. And then it also has some synchronization primitives to do things like have the host tell the runtime environment that it wants to wait until the calculation is done on the device before it continues, and so forth. So you can look for some of those capabilities in the documentation. Now, as you'd imagine, there's no free lunch. There's some additional constraints that we need to be aware of when we're programming a GPU. And one of the most important things that we need to have in mind is kind of the basic underlying architecture of the execution of threads within a block on an SM. The model that is used here is referred to by nVidia as the single instruction multiple thread model. And this is consonant with what we've talked about so far, right? We might have hundreds or thousands or hundreds of thousands of threads that are all executing concurrently. And the performance of those threads is really quite good. There's pipelined execution. You know, those little CUDA processors on the chip still do quite a lot of really cool stuff, so they use pipelining. But they're still simpler than the CPU, as we've described, right? We're going to only issue instructions in order. There's no out-of-order execution. We're not going to do any kind of branch prediction on a conditional. We're not going to try to speculatively execute multiple branches simultaneously. In order to do those kinds of things, we've got to have a lot more control logic. And on a CPU, where we have a small number of cores and a bunch of leftover space for control logic on the chip, that's perfectly legitimate, right? We want to have really low latency execution on the CPU, and those kinds of technologies deliver that. On the GPU, as we've already discussed, the trade-offs are very different. We want to have many, many cores, and consequently, they're quite a lot simpler. So, although we do have fairly sophisticated processors in the grand scheme of things, they aren't as sophisticated as what's going on the CPU. This single instruction multiple thread idea here should be reminiscent of something we talked about when we discussed Flynn's taxonomy, the MIMD and SIMD thing. So this is quite close to what we talked about before as single instruction multiple data. Now that kind of a processor architecture, which is quite similar to what's going on here in the CUDA core, is designed to run a single instruction at a time across a bunch of different pieces of data that we're calculating with. So oftentimes it's multiple like arithmetic logic units that are all ganged together with the same control logic, and each of those ALUs is going to do exactly the same operation, but on different parts of the data, different elements of an array, for example. And that's really quite close to what's going on in a CUDA core. The way that the NVIDIA folks describe this is that they group together these calculations into what they call a warp. This is actually something that they kind of they jokingly are referring to the technology behind weaving. So they refer to this as weaving as the original parallel threading technology, right? Because when you're weaving something, you have threads going in two directions, what's called the warp, and then the weft or the woof goes in the other direction, and the resulting thing is cloth. So they've co-opted this term warp. Well, what's a warp? On nVidia, a warp is a group of 32 threads. When you have multiple threads that are executing within a streaming multiprocessor, the streaming multiprocessor is going to schedule those threads in groups of 32 at a time. So this is the unit of thread creation, of thread management, of scheduling, and execution, right? Everything happens in groups of 32 threads. And those 32 threads are what make up this notion of a warp. So the idea when that kernel gets started, it's going to basically be running 32 simultaneous processors executing the same instruction, the very first instruction that was in the kernel code. So we start at the same location, and then as the kernel code executes on the different processors, they could branch, they could execute different portions of the kernel code. That's fine. Each one has its own program counter, its own registers, so we don't have to execute in quite as lockstep a way as a traditional SIMD kind of an architecture is concerned. So we have more flexibility than we used to have in the SIMD days, but we don't have complete flexibility to let every SP within the SM go at full speed, unless every single thread within that warp was doing exactly the same thing. So if we didn't have any branching going on, we didn't have any ability to call functions or anything like that, and every SP was operating in lockstep with all the other ones, then we could go at full speed. But in general, a warp won't go full speed if any of those things are violated. So here's kind of the procedure that actually takes place when we start doing a calculation in this warp model. So first of all, of course, this streaming multiprocessor is going to get a collection of thread blocks that it's going to execute. It's going to partition those thread blocks into warps. Now this again is, we're operating when we program at the level of blocks within a grid and threads within a block. This is something that's done at the execution time inside the chip to partition these thread blocks into different warps. And it's going to number those threads in order to help keep track of them. Now, once it's partitioned those threads, then there's another piece of hardware here that does scheduling of those warps. So you might have multiple collections of these 32 thread warps that could be run at a particular time. It needs to pick the one that's ready to run and then execute instructions on it. So the scheduler is that piece of hardware that determines, hey, this warp is ready to go, let's run some things. So it schedules the warp to run, and then when it actually executes an instruction from that warp of threads, it's going to execute one common instruction. Now this is the closest that we're going to get to that SIMD model, right? We've got a bunch of different threads, 32 of them in a warp, which presumably when they started up, figured out which portion of the data that they were going to manipulate within each thread. And as long as each of those threads are doing the same instruction because it didn't branch or call a function or anything like that, the warp is going to execute all of the threads at one time. But this idea of a common instruction, if anybody diverges from that, then the warp can no longer have all of the threads running simultaneously because there's really just essentially one control circuit that's responsible for having each of those SPs doing the next piece of the calculation. So if everybody stays on the common path, right, we get the maximum efficiency. If all the threads execute exactly the same instructions in the same order, we're going to get the best performance. Now that is something for you to keep in mind. That's really an important idea when you're trying to get good performance out of a GPU. You want to have all of those threads do the same thing at the same time. That may not always be possible depending on the algorithm. So you could have divergence where some of the threads take the if part of an if-then and the other threads take the then part. So we've got divergence across the different threads. Because there's only one control unit that's responsible for all of the 32 SPs within this warp, what will happen is those different divergent paths are going to execute serially. In other words, the warp scheduler is going to run all of the threads in the then part of the conditional, while the ones in the else part are going to just be disabled. And then it's going to switch and enable the else part and then the then part threads are going to be disabled. So the threads that aren't on the path that's currently being executed are going to be disabled for the duration of that set of instructions, and then we're going to switch to do the other set of threads that were temporarily suspended previously. Eventually, presumably, at the very latest, when the kernel itself returns, those threads are going to converge, and the warp scheduler is going to be aware of that. And if they do converge, it can continue now to execute everybody at the same time, and we might converge and diverge over the time of the execution of the kernel. It's important here to note that the warps are independent of one another. So we can have multiple warps running simultaneously with different sets of SPs within the same SM. And if you look back at some of the architecture snapshots I took in the hardware talk, you'll see that there's different numbers of warp schedulers for different generations of chips. But the divergence that we're worrying about here is only within a warp. If we have two warps that are running on separate pieces of hardware, separate control units that are manipulating different SPs, those two pieces can operate independently. There's no dependence between warps. It's only within the particular warp that we have to worry about this. Now, at first blush, it might seem like this restriction is going to totally kill the performance of the GPU. But because of this characteristic, the notion that the SIMD constraints are really only present within a warp gives us a lot of flexibility to go faster. If we have a bunch of warps that are ready to run, then if a particular warp gets blocked, for example, if that warp is doing DRAM access, the warp scheduler is free to abandon that warp temporarily and switch over to a different warp that is ready to run. What we're talking about basically is doing a context switch from one warp to another warp. Now, context switching kind of has a bad reputation, particularly when you're thinking about it in terms of switching from one process to another at the operating system level. Right? When one process becomes blocked on I/O, for example, the processor is going to decide to not run it until that I/O is completed, and it's going to have to switch over to a different process, which usually involves saving a bunch of state information, right? All the registers in the processor, any other kind of state data that's necessary to kind of temporarily put that first process to sleep, and then it's going to have to load the corresponding information for the new process out of memory, put it into the processor, and then start running it. That's a very, very time-consuming process, so it doesn't seem like being able to context switch at the warp level is going to be a big win. However, the GPU is designed to do this. So what we see on an nVidia part is that the execution context, right, all that information like the program counter, the registers, the contents of shared memory and stuff, is going to stay on chip right there on the GPU for the lifetime of the warp. So once that warp gets started, we're never going to give away any of that context information until the warp is completed. So in terms of switching from one context to another, here's the awesome news. Context switching is free. Because that information is already there on the GPU itself, the ability for the warp scheduler to switch from one warp to another can happen essentially in a single tick of the clock, a single instruction issue time, which is really remarkable. But the point of a GPU with this massive number of processors is to give you high throughput, right? Being able to complete a lot of calculations in a short period of time. It's not focused on latency, it's focused on throughput. So as long as there's something else for the GPU to do, it can continue to deliver good throughput overall over a period of time. So when, in fact, what's going to happen here, when the warp scheduler is ready to issue an instruction, basically ready to skip to the next assembly language instruction that it's executing, the warp scheduler is going to look at all the active warps and choose one that is ready to go and issue the instruction to that warp. And in the very next instruction issue time, if that warp is no longer a promising candidate for continuation because it's waiting on I/O or waiting on memory access, for example, the scheduler can switch to a totally different warp and kind of bounce back and forth between those warps with no cost, right? If an operating system tried to do this, on an instruction by instruction basis, the machine would crawl to a halt because it's just not designed for that kind of state or that kind of context storage. But the GPU is really good at that and allows it to keep something going on at all times if there's enough work for it to do because there's enough warps that can be scheduled.